today we go back to the original set of Maxwell equations, and so let's first discuss the law of induction, or that is due usually Faraday's. That is this one. So as long as we discuss electrostatics, this curl was vanishing, right? That allows us to use the scalar potential. But now, really, so let's write it without the C. If you remember, the full Maxwell equation was really this one. Okay, so it's not any longer true that the curl of E vanishes, because if you have a magnetic field that is now changing with time, then the curl of E is proportional to this change. So that's a very important new information. And just to make clear what that means, let's go to the integral form, right? You remember that if you have a curl, that's correspond to going around with the line integral of this field E along some path C, okay? So this is the circuitation of this vector field, and this, let me take it on the other side, is equal, so let's take the total derivative with respect to T of a surface integral along, let's call it SC, that is the surface defined by this path C, of the normal component of your magnetic field, right? Something like this. So, what does it mean? Actually, if you go around with the electric field and you integrate, right? This is the circulation of the electric field. This is also what is called the electromotive force. That is the force that is generated by the electricity in that circuit. Okay, so sometimes this is called the electromotive force, EMF, right? You know that. And that clearly is just the flux of the B field. So if you have a situation in which the flux of the B field is varying, either because the size of the field is changing, or because the volume, the surface is changing, either one. That's why I put the total derivative, just to remind myself that even if I have a constant, for instance, let's take a, okay, even if I have a constant B field, but I'm changing the surface, right? I'm changing the flux, and therefore, when I take the derivative, I get something that is not zero, and therefore I induce some electric force, right? In fact, this is the most common situation in which actually the B field is constant, but you are changing, in most of the devices to produce a difference in potential to generate electricity. What you do is you're not varying the magnetic field, you're varying the flux of the magnetic field by varying the area intercepted by this constant magnetic field. For instance, you take a constant magnetic field, and I draw, so the force line of this B fields are coming out of the blackboard, right? So I put just okay, so these are many, it is constant in size and also constant everywhere. Then you take a wire, right, something like this, you let this wire go across, and you close this circuit by some metallic wire, a metallic bridge closing this circuit, okay? So if you call W this distance, and say L this one here, and then you start pulling this bridge this way, okay, with a certain velocity. So these are the force line of B. So you see that the B field is constant, is uniform, but I'm changing the flux because I'm pulling this bridge along, so I'm changing the area here. So I can immediately compute how much this electromotive force induced by the change in flux is, because you see that what is the flux here? Well, I call W this, and L is B uniform. So the flux for fixed at the initial moment is just WL times the length of the B field. But now I'm pulling this away, so essentially the change here is going to be what? The WB are constant because this width is constant, the B is uniform, so the only thing is changing is this length, so the derivative is going to change with this so in other words, the velocity, right? The velocity with width. I'm pulling this bridge across there. So in a region in which I have a change in flux of the B field, I found that electric fields are generated. You see, you start out with 0 electric field, but just because then you are changing, you're just pulling this, you induce an electromotive force, so you end up with an electric current going around. And if you have an electric current, that means there is some electric field that is pushing. Now, this is not a far-fetched, this is the basis of our civilization in a way, right? Because this is how we produce electricity. So light, the computer, everything is originally somewhere you produce it this way. You know, like, well, there are many ways to produce electricity, but this changing of the flux of a constant magnetic field is the main production line. And I have here an exercise immediately through how you can compute how much electricity is generated by an electric generator, right? An electric generator is just a wire like this, and then you make it turn in a magnetic field. So because it's turning, the flux is changing. So it's similar to this one, but just you change the cross-section of your circuit, and in this way you generate an electric force, some electric current. So this was the first completion. I mean, we started out with this Maxwell equation. Now we wrote the full Maxwell equation. So this completes this original equation that we wrote down, and the physical meaning is this one. So we are going to exploit this in some examples in a second. And as I said, this is the general idea, that you produce electric forces by varying the flux of some magnetic field. The other equation that is left out, right? The last one was the one about the curl, not of the electric field, but of the magnetic field. Remember, this was the curl of B, and we studied last week. We studied the magnetostatic limit, in which the curl of the magnetic field was equal to the density of electric currents around. But this is not the full equation. As you know, there is an extra term that we already sort of studied in one of the exercises, but it's so important that I want to do it together one more time. So this is the full equation. So this and these two are the two equations relevant for, yes? Yeah, like this. Thank you. So these two are the two equations relevant when you have varying fields. And always remember that it's still true that the divergence of B is 0, and that for the E field is this proportional to the. By now, I hope you know these equations by heart. And but those we already study within the electrostatic, I mean the static limits, and there is no new information that we have to understand here, because they are the same equations even if you have fields changing in time. But here we now are looking at these two new terms and what is the physics of those. So really, all these equations, except for this one, were already known before Maxwell. Before Maxwell wrote his equations. In fact, you see, this was essentially studied by Faraday, and these two, okay, this is essentially Coulomb law, we said many times. This is the reciprocal of Coulomb law, that there are no magnetic monopoles, right? So there is no magnetic charge. Magnetic charges always come in pairs, essentially, because the magnetic field is generated by current, not by charges, magnetic, whatever that magnetic charge is. So let me just reiterate how Maxwell identified this term, and the way is like you did in one of the exercises, is just that without this term, if you consider just the original equation, this one, right, and you take the divergence of both sides, right, so that you get here the divergence of C square curve B, and on the other side you get the divergence of J, right, 1 over epsilon, the divergence of J. Now the divergence of a curve, right, remember, is just 0. So from this very simple, that I believe is what Maxwell actually did. I mean, he just took the divergence and realized that if this is true, because of the property of the curl of a vector, the left-hand side vanishes, therefore the right-hand side vanishes as well, but that implies that the divergence of J is equal to 0, okay, and that's okay, as long as you have a static situation, but if you allow changes in your charge density, you know that this is the correct equation of continuity. That is just another way of saying that the charge is conserved, because you understand this equation is just, well, it's called continuity because it's true for any flux. I mean, if you have water, this is true for water. If this is the density of water in your faucet, if you see that the amount of water is changing, that's because it's flowing out from somewhere. Or if it's increasing, it's flowing in. So the flow in or out, whatever, is quantified by the divergence. Remember that you can always go to the integral over the surface, and this will give you so the current coming out. And of course, inside you have a certain density of charge or density of matter or whatever. And if that is changing, the two are related by this, because otherwise somewhere you have a destruction of charge or of matter or whatever, or fluid or whatever that is. So this is the equation of continuity, and as I said the first time we discussed it, it's a local conservation, right? Because really it means that one charge that is moving out, it really goes across this surface. It's not that you destroy the charge here and create another one equal far away. That still will give you, it will still tell you that the total charge, say the total derivative, is equal to 0, that it doesn't change, right? But it will not tell you this. This is stronger than this, okay? Anyway, so you see this is equal to 0, but really it should be equal to this term here. So this was the problem, and if you add this term, what happened? That you have a new term, an extra term, that is the divergence of dE dt, right? So as usual, we can switch those around, assuming that everything is okay. And of course, the divergence of E is this thing here, right? So you get 1 over epsilon d rho dt. So now 1 over epsilon naught d divergence of J is equal 1 over epsilon. I think here there is a, right, a minus sign, and or is plus, no. Because it's on the same side, okay. So it does matter, sorry. And so indeed you get this one here. So in this case it's written like this.
So I think, so
Yes.
this thing is true even if the charge density is not static, right?
Even if it's not?
Static.
Yeah, this is in fact is when it's changing with this one.
Yeah.
Yeah, this is always true.
I mean, if we didn't like.
I mean, this is equal to 0.
No, the divergence of J is 0, yeah.
The divergence of this.
Is 0, even if the charge density is not varying with time. I mean, there are cases.
This is 0 if the density of charge is not changing.
I mean, yeah, but even if it is changing, it can be 0. For instance, if you take the volume to be like large, and then
Large meaning?
I mean, at which the effect of the electric field or something is 0.
I'm not sure I follow you. I mean, this it's like this. I mean, it's really. If this is constant, then that means that nothing is going out or nothing is coming in. So then it's okay. That means that if you take the surface integral of this J, it gives you 0. So it's true that divergence is 0, but otherwise it's not.
Like if we take the surface to be like at infinity, then.
Well, the infinity, that's a very difficult thing to. Just let's say.
The charge is localized, then this thing can be 0, even if. Yeah,
No, but if it's at infinity, it's flowing where? I mean, if it's an infinity, it's not. I mean, there is no place to flow out from, right? That it means that I have included everything. If you do that, then okay, yes. But don't think locally, right? I mean, think locally. This is it's a powerful statement about this fact that if this is changing locally in point X, that means something is coming out or something is going in. Okay, but this we already knew. And by the way, that means that the equation of continuity it follows now from Maxwell equations, right? That's nice. So what is left? This it has a name. Maybe displacement is current. Okay. It's really, it's what. So it seems like a detail, but this is really the terms that allow the solution of Maxwell equations to produce the electromagnetic waves, right? Because you see that complements this. If you have a varying B fields, then you induce an electric field. But then if you have a varying electric field, then you produce a magnetic field, and so on and so forth. And then you start seeing all these waves produced by oscillating electrons, right? Okay, so it's really the beginning. In fact, that was the next thing, the next big contribution by Maxwell, beside writing the correct equations, was to solve in some condition, under some assumptions, this equation and show that in fact they had solutions that they were waves. And not just any waves, as we will see, but light waves, moving with a speed that was controlled by this, how is it? Like this, right? That explains how come that these two, I mean, in principle, completely unrelated properties of matter are linked through the equations to the speed of light. And I mean, up to now, we haven't seen any light, right? We are just talking about charges, magnetic stuff moving around, but there is no light here. I mean, you really need to study a little more these equations to see that they actually include light. But we are not ready for that yet. Well, actually we are, but I have to cover some other materials that you may need to know, like as we went through electrostatic and magnetostatics, that, I mean, they are not essential to the understanding of the Maxwell equations. They are just limiting cases, but nevertheless, they belong to the common knowledge of all physicists, so you must know them as well. So let's go back for a second to Faraday's law. And as I said, if you make something that intercept a variable amount of B field, then you induce some electromotive force. And the standard thing that you so this is the exercise, so homework for Monday. This is taken from the same book where I'm taking most of these exercises. So, and so first try and solve them if you can. Go to. Did you find a copy of that book? I assume yes. Because I tried to check them all out from the library, but clearly one was not there. So now they are asking me to return the copies. The library wrote to me asking to return the copy because somebody, that I guess some of you, wants the book. But of course I'm not returning the book until I'm finished. So, but okay, but it's okay. I mean, it's no secret. I mean, it's not something, it's common knowledge. But first try really for your own good. Try to solve it, and then only if you're stuck, right, go to the book and see the solution. So if you go to that book, you see that the simplest gizmo that you can define is something like this, right? You have two wires going around. I'm not very good at something like this, right? Two wires like this. You connect here with a circuit. You know that when you draw this, it's like a resistance. So this is a circuit across which you can measure some potential, electric potential. And if you have here some constant magnetic field, it's like the one I draw there, but this is more realistic, right? Because it's not very practical to pull a wire. But it's very simple to have these things turn around with a certain angular velocity omega. And you understand that as this thing turns around, it intersects a variable surface, right? So you have that the flux of B, even though B is constant, B naught, the flux is not, right? And this is really the basic of most electric generators. So the homework, I guess, is about an electric generator, a motor, as it's called. And so, of course, the question is, how do you make this turn, right? Because, you see, the energy is conserved, so it's not that, otherwise I would produce electric energy out of nothing, right? But you see, to generate this current in the loop, you need to turn these things. And how do you turn the things? It means that you need energy from somewhere else. For instance, in Italy, many of these somewhere else are you know, they use water. You collect water through some artificial lake. Then you have big pipes. Then you let the water fall down. So essentially, the energy comes from where? Potential energy, gravity from the previous class. So you let the water fall down, it hits some turbines, right? Those start turning, and by turning, they start turning an electric wire or something more complicated, I'm sure. The concept is this, and by intersecting some magnetic fields, that generates electricity, and then this arrives to us, and we can watch TV and all these things. So what I want you to try and compute is what is the electric, what is I? So what is the electric current induced if you have this? So call like the book does. You call A this this area, right? So you have a B field. This area is A, so it's easy to compute the flux. And then remember that I is V over R, where V is the potential, so is the drop here. And this can be computed by using this Maxwell equation, okay? So compute this I. It's going to be a trigonometric function of sine or cosine of this omega t, right, clearly. And then maybe you can also remember that, so what happened to this current going through, right? Essentially, at the end, it goes into heat, right? Because if you have a wire and some electricity going around, it's heating up your resistance. So you can compute the heat generated, and well, we haven't done this, but probably you remember that that goes like the square of the current, right? So this is essentially the energy dissipated, and in heat. So please compute also this. You have to compute this, and then you can compute the average of this by simply taking this, right? So this is going to be a function of t because this is a function of t. So if you take the average defined by the integral over a period divided by the period, then how much is this? So three things. 1, 2, and 3. Then on Monday we solve it together. Is it clear, or can I erase it? So that's nice because, I mean, if you understand this, you understand most of the energy production, electric energy production that is so important for many. Okay. In fact, I think I want to give you some more exercises on these electric circuits because it's boring to do it on the blackboard, but they are nice as exercises. So I'll give you 2 more exercises on these electric circuits. I mean, they're not really, usually they are part of a more basic course on electromagnetism, so I assume you have already studied them. But the physics follow for the Maxwell equation, even though, I mean, when you have to build an electric circuit, you don't write down the Maxwell equations, but it's the same. But before that, because so if you have an electric circuit, you know that you have the resistance, right? And we already studied the other property of a circuit, in fact, of any conductor, that is the capacitance, right? The C. And there is a final thing that has to do with the magnetic field, that is the inductance, right? So let's just discuss briefly this last but not least important property of a circuit. So that has to do with the fact that if you generate a B field, that sort of reacts on your circuit. So the basics, you remember that we studied, let me see if I can draw this. We studied the solenoid, right? This is it's a wire okay, a coil with some current that I call I2, you'll see why in a second, and we study, and this has a magnetic field, right, that is essentially constant inside, and that we already study and we understand it. Very simple way to, in fact, this is the simplest way to produce a uniform magnetic field, right? So the next thing you can try is to have another wire, another coil going the other way around, like this, and this with the current I1. So you see now what is, so if you look at coil number 1, right, this generates a magnetic field inside that we already computed. You remember it was 1 over epsilon naught c square, that is just this mu that if you want to call it mu naught, and then it was proportional to, so if you call the number of turns per unit length of this coil, so divided by L, the length is L, right? So the number of times you wind up this coil is N1 over L, and therefore you remember, right? The magnetic field is the first example or the second example I discussed in magnetostatics. If I have a steady current going around the coil, it generates inside a B field that has this intensity. So that's the solenoid. Now, what happens if this B field that I'm generating varies with time? Right? Now we make the next step. For instance, I allow the current that is inducing this field not to be constant. I vary the current. Right? Why not? I just discovered that is going to induce an electric field, so immediately you want to vary this I1, so you are inducing a very magnetic field inside this coil. And then if you look at the other coil, because you have a very magnetic field inside, it's not just sitting there. You have an electric field, an electric motive force induced because of the equation that I wrote one blackboard ago. So let's do it. So the electric motive force in coil number 2, I call it E2. Okay? And it's going to be how big? Well, it's going to be, we just computed before, it's going to be proportional to the area of this coil. Let's call it S. And then, it's S times the number of coils that I have. So it's N2 now. This N1 was the number of turns in coil number 1. So this cross-section S, and then the time derivative of the B field that is going to be the time derivative of this. Now there is an important point here that I should put a minus here. Okay? Why? This is called the Lenz's law, that always there is a minus when you are inducing some electromotive forces. Okay, these electromotive forces itself should induce something that goes against the original mechanism. That's why you put the minus here. Why? Because otherwise you will have a sort of catalytic process in which you start with the little things, you generate a varying field, then this generates another field, and then it becomes bigger and bigger without any effort, right? That cannot be. So it's a manifestation of the conservation of energy. Okay, it's called Lenz's law. We'll write it again. So this I can write because I have what is B. So I have minus N1, N2 divided by this epsilon naught C square. This area S, cross-section, whatever you want to call it, the length of this wire, the total length of the wire, and then a derivative of your electric current. I don't know. That is, you pick how you want to change the current, and so by changing this current, I induce through the magnetic field an electromotive force in the other one. So you see, I start this one start with 0 current, for instance, but because I'm putting a varying electric current in coil number 1, I'm inducing a current also in the other one. Okay? You know or yes? Or do I say you? Do you understand or not? Okay, you're tired. So this is called mutual inductance, right? Because you are inducing something in the other field through the variation of the magnetic field. And you understand that is reciprocal, right? I can write as well a 1 here. So if you see, this is a constant that only depends on the geometry of your coil. So this is called the mutual inductance. So it has nothing to do with the current you're putting in. It just depends on the geometry of the wire, like the inductance has to do with the geometry of a single wire. And so, so this, let's call it M21, and this there is the equivalent here that is MI2 dt. So this coupled system of 2 coils, they can induce to one another electromotive forces proportionate to this coefficient that we call mutual inductance, and then proportionate to the change in the electric current that you are putting in. Now this can be compared, remember, if you had just a single coil, I mean a single coil, even there in the coil, right, you get a current induced that is just proportionally to the change in current, right? Even if I have just one current, just one coil, and I vary the current in the coil, I generate this magnetic field that is changing, and that magnetic field in the same coil itself is generating an electromotive force. And notice that now it's clear why you should put a minus sign, because you see, it's not that by varying a current you get out a larger current. I mean, it would be nice. We wouldn't have to buy oil from anywhere, and we will just start with a little coin and power off the entire nation. But the sign here, that is this Lenz's law, tells you that you are inducing an electric current that in a way goes the opposite direction than the original one. So it's opposing the effect of the first current. That's why it's a form of a conservation of the energy. Okay? And so this is a sort of a resistance, this inductance. So this is the inductance. So this is the mutual inductance if you have 2. This is for a single coil, so that is the inductance. And again, it's just a characteristic of the geometry of your coil. You see, it just depends on these numbers, number of times you go around, and so on. And so if you want, this coefficient here is the if you write the simplest circuit, right, you have here some voltmeter, and you have a current going around. Now this is the simplest. It just have this L, right? That is this inductance, and then the drop in potential there is just L di dt. So this is sort of, but I'm sure you already know this. This is a sort of the basic circuit if you don't have any resistance or capacitance in the story. And you see, it's kind of nice because you see this looks like, I'm saying this inductance is like an inertial term in the circuit. You see, it's like if you think of the potential as a force, you see this is the current is like the velocity. So this is like an acceleration. This is like a mass. So this looks like Newton's law, and in fact, so L times I is a sort of momentum, and in fact 1/2 L I square, if you remember, is a sort of the energy of the circuit that looks very much like 1/2 mv squared. Really, it's not just a gimmick. It really has, because of this sign, it really is a sort of inertia in the circuit. I mean, you change the current, you auto-induce an electric current in the circuit, but it goes in the opposite direction. So it's making harder and harder to. So having said that, let's see what kind of. So we have all these sort of circuits, and it's nice to solve them because they are the ideal place where to solve differential equations. And really, if you remember your harmonical oscillator, these are just variation on the harmonical oscillator because, as you will discover by doing these two homeworks, essentially what you have are differential equations for harmonical oscillators that are essentially damped oscillations, right? Because you see that you have damping terms depending on the resistance and the inductance, okay? So, okay, maybe you already know this stuff, but on Monday we solved them together. So first study the simplest circuit. So the simplest circuit is the one without a capacitance. So I guess you put a V, I don't know, something like this. And here you have, so the resistance usually is like this, and the inductance is like a spring for some well-established convention. So this is L. So this is the simplest circuit. So you can write the differential equation for this and solve it, and then we discuss the solutions, okay? And the next step, so this was one. The next step is when you have, in addition to a resistance and an inductance, so you understand this has to do with the magnetic field in here. This is more to do with Ohm's law and this kind of stuff, and the capacitant has to do with the electric field. So if you have a capacitor, so I guess I should put it here. So this is C, then you have R, and then you have the spring. So now you can write the new differential equation because you have this extra piece that I wrote there. And so again, then write the differential equation, then we discuss the possible solutions. Clearly, this looks very much like the harmonical oscillator, and if you start with this with a fixed value or something, then or 0, then you have just the damped harmonical oscillator. But if you apply here an external potential, like an external force, for instance, try an external oscillating force potential, like a cosine or a sine, then or e to the I omega t, even better. Then it will be a driven harmonical oscillator, right? And you remember the solutions are those that we already studied. But it's nice, I mean, the same equations come in very different situations, because they were penduli or springs, and here you have a sort of electric analog of those mechanical systems, but they have the same equation. So if you remember the one you solved for the harmonical oscillator, then okay, there is no extra work here. That's nice. Okay. So now we are back to the Maxwell equations, so we can do. Well, of course, we can try and solve them. That's the aim of this entire course, study the solution of the Maxwell equations. We already studied some simple solutions when there was no time variation in the fields, but pretty soon we are going to look at the full solutions. But before we do that, we can study something a little bit, we can learn something without having to know the solutions, and that, like in mechanics, has to do with the conservation laws. So we do expect here, as we did for a mechanical system, that there is conservation of the energy and of the momentum, right? Why not? It must be. The conservation of energy is always true. So even this system, made now not of particles and forces, but it's just made of fields, must conserve the energy and the momentum. So let's see how we understand this. How do we proceed on this in this case? Of course, I hope we are going to recast this also in the Lagrangian formalism, obviously. So there will be a Lagrangian for the electromagnetic field, because that's, I think, is the reason why, well, one of the reasons of this class. But in that case, it would be even easier to see that you have a conservation of the energy. But at this intermediate level, it's useful to look just at Maxwell equations and see this conservation. Also because this allows us to introduce new concepts that are useful in the visualization of the physical problems. Some I already wrote for you the energy density, remember, of the electric and the magnetic field, right? They go like the square of the field intensity. So we are going to use that. But let's first start with the, so if the energy is conserved, that means I can start from the variation of the energy, right? So this is sort of the power, right? If you take the derivative of the energy, that's roughly. And how does that go? It's essentially for if you have a volume where you have an electric field, this goes like G, the density of current times the electric field, right? This is essentially, do you see that? Because it's like F, the electric field is like F, it's like the force, right? And J is like the velocity. So the power is F dot V. So this is really the change in energy that you have because of the presence of an electric field in a given volume. You see that, or? I see. Do you see it or not? Otherwise, you have to believe me. That is as good as seeing it. I mean, if you have an electric, I mean, F. This is the, is the time derivative of the work done, right? So that's also known as the power. And you see, it's the same, because the electric field is just sort of, for take a single charge, right? It's just something like this. Okay, you should define more precisely the limit, but, and then the current, as we said, the current is just the charge times the velocity, if you have just a single charge. So you see that this is the change in energy if you have a single charge. But of course, this is more complete because it's a local change due to a charge density, not a charge density, a density of electric current. No, not even that, because how it's called, of the current density times the value of the electric field there. Okay. So now you see it, or maybe not. So the first question is, how about B? There is only, but you see B is always orthogonal to the velocity, right? Because again, if you take a single charge, you see that the V cross B, right? is I mean, the force is like this. So you see, if I take F dot V, right, that's a very important property of the B field. The B field, in a way, is not doing any work. It's a really lazy guy. I mean, it's just sitting there, and the only thing to get work out of the B field is you have to vary the B field in time, because then he calls some electric field. The electric field comes and is producing this. Okay, so that's very important. So the B field is not there for this very good reason. That is not. So just remember the lazy guy, right? Everybody remember that. And then you see that this is all there is to worry. So now I'm going to do one of those long blackboards in which from this I derive everything else, okay? So I hope to do it. So what I want to see is this is how to say, is the change in energy inside this volume, right? We all agree on that. Now I want to rewrite this all in terms of electric and magnetic fields, right? And see what is conserved. I mean, how this is changing in time and as you go out of the volume. So I'm going to deduce some sort of conservation law like we did for the electric current and the change in current, in the electric current and the change in density of charge. So let's see that. So first I want to get rid of this J, because I want to assume that all the J's that I have around are produced by electric or magnetic fields, right? Because I only want to study the magnetic and the electric field. So I use Maxwell equation that they tell me that J is equal, remember, epsilon naught C square, the curl of B, right, plus this famous, actually minus this famous Maxwell displacement current. So you see this way, I take Maxwell equation, I replace it inside this integral, and this way I have everything written in terms of electric and magnetic field. Because this, from the point of view, is not a fundamental concept. This is the current induced by these electric fields. This is always true, even if you have the current in the wire through which this light work, even there you should think of the electric field producing that. So then if I do this, substitution, you see I have this integral over the volume. Let me pull it out here because it's going to be, and then I take all this term here, right? So you see I have epsilon, sorry, epsilon naught C square. Now I have this, so I have E, let me pull it on the left, dot this curl, right, is this first term, and then minus this epsilon naught, this one here. So I have E dE dt. And I've used this Maxwell equation. So that's already almost what I want, because I have everything written in terms of my electric field and magnetic fields, but still it doesn't look that great. It doesn't look that great. So in particular, this looks nice. Why I say it looks nice or bad? Because I know that, yeah. At the end of the day, I want to write, I already know that the density of energy, remember, it was 1/2 E square plus B square, right? With the, I guess you want an epsilon naught here and therefore a mu naught here. That is 1 over epsilon naught C square, right? So this is already something I know, because here I'm looking at variation of the energy, and that is the energy of the field, electric and magnetic field. So this piece looks nice because it's already, you see, sort of the derivative of the density of the electric field. This one is a mess. I want to massage that term, And the way to do it is to use this, the usual one of those that I gave you, the photocopy of this famous, when you have three vectors. Now it's like the, right, is like that this is equal to b, I can never remember this. Right? So I take this term and I rewrite it in this form. Why? Because you see this, again, by using Maxwell equation, right, this is just dBt, right, the partial derivative of the B field with respect to t. So that's fine. So you see already I have two terms, so let me write it down here. This whole story, this already is a term that looks exactly like this one, that is the derivative of u. And then I'm just left with this term here. Okay, so I have a minus here, a minus there. So let me write it this way. Minus, I pull it outside, on the other side. So I get that my original volume integral over the scalar product of the density of current times the electric field, right, is equal to this, this integral over the same volume. So you see this term here, right, and this term here, they are exactly, right, this is mu naught, this is epsilon naught, so it's just du dt, where u is this one. Huh?
It's 1 over mu naught. B squared over mu naught.
Yeah. Actually, in the books, you will find this. That, of course, is exactly the same if you are in the vacuum. Right? In fact, this is maybe because D, remember, in the vacuum is epsilon naught E, and B, I guess, is mu naught H. Of course, this is also true if you are into a macroscopic medium, but then it's not any longer true that D is just equal to, is just proportional to E, and neither is H proportional to B. It's more complicated. We discussed it the first week, and as I said, I don't want to enter into many details there. But anyway, I mean, this is true in vacuum, and this is always true. Anyway, you see, we are almost there because but then I have this extra term plus, because I pull everything, the minus, I pull it on the other side. I have the divergence of this E cross B. So is this a mistake, or so this is correct? You know, the change in energy inside this volume is the change in energy density of your field. That is exactly what you expect. But you have also a flux. You have the flux of this vector here, right? And this vector here is called S. Is the Poynting vector that you may have already heard about, and is perfectly fine because it's exactly like the continuity equation for the charge. You see, you have a volume and you study how the, so here, if you want, this term here is the change in energy, right? So the change in energy in this volume can be either because actually the fields are changing, right, in size, and so they decrease or they increase, And this is taken into account by this partial derivative. Or because there is a flux, you see this is a divergence of this vector, so there is some flux of these fields going out or in, and this is quantified by this Poynting vector. That's really nice, because you see, we are talking about fields, but it's very much as we did for the charge. So you have a sort of a flux of this new vector that is the cross product of the electric and the B field. So either they go out this way, right? You may have some force line. So you compute the flux of this Poynting vector, right? And then maybe this the value of this field is also changing in time. That gives a contribution to this term. And they together, they tell you how the energy is changing in that volume. One way to measure this is to put some charged particles. You put some charged particles inside, and if the field, so then is the change of the mechanical energy inside. So either they move faster or they move slower, or and this, if they move faster, that energy must come from the field. So it's taken into account of these terms, okay? Or the fields are going out, and then it's taken account by the Poynting vector. Is this clear? So now we have a new vector that we will use again, because it quantifies how the energy is moving in a given portion of space. And let's see some example, so maybe this becomes a little clearer. So I looked at two examples. Well, really just one example. Well, so example number one is sort of this. Let's go back to the single wire with some current, right? Some density of. You remember this one has a magnetic field, right? So at the point here in space around, you have a magnetic field that goes like this, right? It's tangential to this circles, right? Then here you also have an electric field, right? Simply because you have charges here, so you expect, and the electric field is going to be like that. So that's the general setup. So we have a wire, like there are many in that wall, or there, and some electric current going, and then you from outside, from here, I have a B field going like this, right? If the wire goes like that, and then I have an electric field in the same direction of the current in the wire. So in which way is the Poynting vector is E cross B, right? So with the usual rule, you know this rule, right? So in this case, the Poynting vector is like that. Now you see that because of the conservation of the energy, you have this electric current going along this wire. And as I said before, because you have electrons running into this wire, you dissipate energy into heat. And you see, where does this energy come from? Right? Essentially, you can look at this as the energy is flowing along the Poynting vector into the wire, and then is dissipated by the heat.
So it's just kind of the energy carried by the radiation, right?
No, by the field. There is no radiation here. We will come to radiation. But at the moment, everything is moving very slowly, so there is no any waves, there is no radiation. It's just that because you have this wire, you put some energy in the field, right? Simply because you have. Then slowly this energy is dissipated because the wire is consuming energy because it's heating up. Then the heat is irradiated around, and then it goes away. Maybe it's even the next example. Take the capacitors. I have here a nice. Take our capacitor that is the main characters of many problems, but I mean we didn't have time to do that many. But anyway, it's nice because it's a situation in which so the capacitor means that you have all these little charges on the two sides of this, right? And so here I'm charging the capacitor, right? I'm start from 0, then I start charging, increasing the charges on the two sides, right? So you know that I'm generating an electric field, right? Inside here, inside the capacitor. Maybe I should draw it like this, right? So now that I have some tridimensional, so I start charging the capacitor. Let's say that this is A, the radius here is A, and the distance of this capacitor is H. You understand that, so I have charges here, charges there, so I have an electric field. So here I have an electric field, and I'm charging the capacitor, so I have a varying electric field. So I have also a B field here, okay? So this is plus and this is minus. Let's start charging. I mean, if it's static, there is only electric field, but because this electric field is increasing with time, I'm inducing a B field, and therefore I have my pointing vector that again is pointing toward the center. Okay, I can even quantify this because what is the energy of this capacitor? Well, the energy of the capacitor is epsilon naught divided by 2e square, right? It was written there. This is the density of energy, so I have to multiply by the volume, I get the total energy of the capacitor. The volume is pi a square h, right, this distance. Okay. What is the magnetic field that I'm generating? Because I also have a contribution there, right? Well, I have to use c square curl of E equal dE dt, right? There is no B. So there is no electric current here. It's the vacuum inside the capacitor. So you understand that, so I do a circuitation, I go to the integral form, so I get 2 pi A C square B, the B is the same everywhere, so I've done this integral, 2 pi A C square B is equal to this E dot, a derivative of E, again, times the volume inside, that is, again, pi A square, but that's it. Not the volume, the surface of my circuit. So you see I have a B field that is going to be A2C square E dot from here. So you see that the change in energy inside this volume is going to be the derivative of this, right? So you see that it's just epsilon naught, then the 2, so I get pi A square, this H, E naught, right? what is the Poynting vector? Well, the size of the Poynting vector is epsilon naught c square E cross B. In these units. Before I just sort of neglect the units. So it's E cross B, but B is this. So if I do it, you see I have epsilon naught c square, then E times A to C square E dot. That is, so C square, so I have epsilon naught I have factor 2 and what is the flux of S in going in? The total flux is pi A square, right, times this this here, so it's pi A square H epsilon naught E dot. So this is the total flux of S. Is this clear, or? What is the flux of S is given by this, right? Then the total flux, so S is pointing inside here, so the total flux is I must multiply this area. So this area is 2 pi A times H. So I have to multiply this by 2 pi A H, right? So you see psi squared, then 2 goes away, and I'm left with this. So you see, that's exactly this term here, right? Yeah. Well, here everything is orthogonal, so I can just take the moduli. I mean, you see, they are like this. Right? And I'm looking at the flux through this surface, so I can just take the absolute value of S. That is what I did. Because S is orthogonal to the surface somehow. So there is no angle. The normal is already normal to the surface I'm integrating. So you see, this first of all checks. You see, the change in energy inside is exactly the flux of the Poynting vector going into inside. So what is going on? Where is the energy coming from that is charging these things? Well, you have to draw the force line in a way. You see, because it's like you had, no, like this. You had all this force line outside because of the charges, and this part of the field is flowing in or out. And because it's flowing, you see, the flow of the field inside the capacitor is exactly equal to the increase or decrease, depending on the sign, of the energy inside the two faces of the capacitor. So you see, that's the correct way of seeing this process. Mm-hmm.
Why do you use the distribution? The volume distribution? Why? Because there is just a capacitor. We can't use the stochastic distribution.
No, here I use the volume to compute the density of energy. I mean, in this volume, you have U, the density of energy due to the field. So there I have to take the volume. On the other hand, the flux of the Poynting vector is coming from outside as it crossing this surface. So there is just the surface. So this was this surface, 2 pi AH, and here was the volume pi A square H. And the two matches. So as you are pulling energy from the fields outside, they flow inside this, they are producing this larger electric field inside, and the Poynting vector is correctly telling you how the fields move in such a way that you have the conservation of the energy. So I hope that so from this point of view, what I mean, it's not that the energy is coming from the wire and producing this difference. No, I mean, because you have the wire, you have all these fields around, and the energy is coming from the field inside to charge the capacitor. So that's the correct way of looking at the.
Why? So where we can find this, because we know to get the B, the velocity has to be variable. Where you
No, B comes because I'm charging this, so the electric field here is not constant, is increasing. So because so that means this is changing, so I'm producing a B field. This is the B field I computed. So this B field goes into the definition of the Poynting vector. So you see they. So that's the conservation of the energy. And how about the momentum? Also the momentum is conserved. Of course, you have to define what is the momentum of your field. So again, well, I don't know. Again, the procedure is the same. Now, instead of looking at the change of energy, I look at the momentum, right? The change of momentum. So that's the force. So what is the force in this local definition? The force is, of course, is Lorentz force. But this is for a single charge. So for a collection, for a distribution of charges, this is the integral of a volume of what? Rho E, right? You replace the single charge by the charge distribution, and here you replace the velocity with the current cross B. So this is the force, or if you want the time derivative. In fact, I can write this is dP dt, like the force, where P is the momentum. And again, I can think of this P as the P mechanical, so I put some particle there. If they are accelerated, that means that I have this action due to this field. And then again, I massage these two terms by using Maxwell equations in such a way that some quantity I know appears to give meaning to this equation. And so this is epsilon naught, the divergence of E, right, this Coulomb law. And again, I replace J by, well, now I decide to use mu naught instead of epsilon naught C square. So this J is the curl of B, right, minus the time derivative of the electric field. So the two Maxwell equations. So if I do that, I get, so if I do that, so these brackets become what? They become, so no, maybe it's nicer to put epsilon naught C square, right? So that I can pull out, let's pull out epsilon naught. Then I have, so the first term is just E times the divergence of E. Then I have two terms, plus, so I pull out the, so I have, so plus B cross dE dt, right? Because I have this term here that is minus epsilon naught dE dt cross B. So I put B across, the cross product is antisymmetric, so I get this term with a plus. And then I have also the other term. Now I put a minus C square B cross this. Okay. I pull the B in front, so I get minus B cross J, and then I replace J by these two terms. I get this. Now, this term here is just what? Is minus dt, the Poynting vector, that is this. You see, if I write, I want to extract somehow something similar to the Poynting vector. So I write this E cross B. So this is equal to this, but there is a term that is not there, so I have to add it. That is E cross dB dt, right? This sum is equal to this. Do you see that? Because you start inside. First it acts on E, it gives you this. Then it acts on B, and it gives you the other term. And this one is just minus the curl of E. You see, it's like a game. You use the Maxwell equation all around. Okay, so I can rewrite that with the curl. And also, to make things easier, I can always add C square B times the divergence of B. Why? Why can I always add this term? Because 0, I can always add it. So I have this plus this plus this plus this and plus this. So I can start collecting. You see, I have the divergence of E. I rewrote it. So if I collect, I get this epsilon naught. Then I have E times the divergence of E plus this term here that is 0, but I put it there because I have some idea that will come handy. Then I have this term there minus the this one, no? Minus E cross the curl the curl of E, and then I have this term that is minus C square B cross the curl of B, right? And then this term here, that is the one that I extracted, that I pull it out because this is what I want to keep to the end. Okay? We are almost there, so just give me 5 minutes. So so let me call this part here the rest, meaning that is something that I'm not sure what to do with. And you see that now my change in momentum, the change in mechanical momentum, is equal to that term that somehow I know what to do. So let me pull it. So this I get dp dt plus this term here that you see I can write as d dt, the integral over volume of epsilon naught E cross B, right, is equal to the rest, this stuff here. Now this is nice because it looks like the Poynting vector almost, right? So I think I defined the Poynting vector as is always this question with the constants. I think so. You see, here you have your density of momentum of the electromagnetic field, right? That was this vector defined by E cross B, or in general E cross H, if you want to do it. So this part here is nice because you see the change in the momentum of the mechanical momentum plus the change into the momentum in the field, and this is part here, right? This has to do with the Poynting vector, is equal to do all this stuff that I still have to understand what it is. But this is, so you look at the Poynting vector as the momentum in the field, and this is produced by this change in this quantity that I still have to. So how can I write this part, the rest, that I'm not sure why? Well, I should write it by component. This is clearly a tensor. You see that is a tensor because it has several components. Is
Divergence of B square plus B square.
these two?
No, just pick the E field and the B field separately. Just
No, I mean,
do the-
this cannot be reduced further, I'm afraid. You see, this is a derivative of a tensor. Take this tensor, T alpha beta, defined this way, epsilon naught. Then I put here the component of the electric field, E alpha, E beta, plus C square components of the B field, minus, you see, this part here is like the, so let me put it here, minus 1/2 of E dot plus C square B dot, so D alpha beta. Consider this tensor. Then if you take the derivative, if you take the sum over beta, the derivative of the with respect to x beta, some direction of this tensor, okay, this is exactly what you have here. Therefore, this term that is missing, the rest, what I wrote here, can be written as the this integral over v, right, of this sum over beta dx beta t alpha beta, where t alpha beta is defined by this. It's defined by this definition here. So now you see that the change in momentum, the momentum is flowing, is given by this integral over the derivative of this. But you see, this I can use, you see, this is like a sort of a divergence of a tensor. So I can use Gauss' theorem to write this volume integral as an integral over the surface of the normal component of this tensor across the surface. So that's nice because you see, you have here the flux of the Poynting vector, and this other term quantify. This is called the flow. You see, these are is like a stress tensor. In fact, this is called Maxwell stress tensor. that gives you the components of the electromagnetic fields, okay, under stress, and the change in the momentum in the system is given by this surface integral, that is the flux of this stress tensor across the surface, identified by the volume over which you are integrating. Okay, so if I call this could be the P of the field. So this is the momentum of the field, right? The integral of this density of the Poynting vector. So you see that the change, the sum of the change in the mechanical momentum plus the momentum of the field is given by this integral over the surface of the stress of Maxwell's stress tensor. Okay, so that's the conservation of the momentum. And as an exercise, you should try, yes, and write the component of this tensor. So make a matrix, epsilon naught, and write all the component of this tensor. So you can call U, I guess I call it U, this guy here. Okay, so we have seen that by introducing this new vector, this E cross B, we can describe in a sort of economical way both. So you need the density of energy for the fields, and of course this momentum of the field, and then you can describe the conservation of the energy and the conservation of the momentum. Okay, and to do that for the momentum, you have to introduce this further concept of the Maxwell stress tensor. That I mean, this is completely. If you take a solid, I mean, or a fluid, this is completely the same things. There too, you have a sort of a stress tensor, right? I mean, that if you push something, well, this is too solid, but if you push some jello or some stuff, you have component of your push, right, that are described by this tensor. Then you have the total momentum of this displacement that is this, and there too you have the conservation of the momentum, and in fact also of the energy. You see, the fact that you have all these tensors, you always have to think of this electromagnetic field in a sort of, it's like a jello. I mean, it's a very strange thing. They live in a very thick medium, right? Because you see, they have all these components. It's not the vacuum where you have the electromagnetic fields. It's not vacuum at all, because to understand these fields, you need to think of some fluid that is very dense, okay? And this will be confirmed when we study the waves, and you will see that the electromagnetic waves are transverse. They are transverse waves. That means they oscillate transversally to the direction of motion. Okay, that's really surprising, because I mean, a wave is a displacement of a medium, right? So for instance, my voice is the displacement of the air, right? They are mechanical wave, but this is you see, the air is very thin, and therefore waves are longitudinal waves. That is, there is a compression of air like this, right, in the same direction of the propagation. You understand that? You know that. But the electromagnetic wave in the vacuum is not like this at all, because it's oscillating perpendicular to the direction of propagation. So if it's going like this, if I turn on the light, it oscillates like this. You see, it's like the pointing. You see, the pointing vector that tells you how the momentum is flowing is orthogonal to both E and B. So they are oscillating like this and moving in this direction. That transverse oscillation are only possible in the physical world in very thick mediums. Like if you hit something like this, you excite a transverse mode that propagates along, but not in the air. It's almost impossible in the air to excite a transverse wave. So that's really something that still is completely hard to understand, because now you think of this oscillation, of this propagation of the fields in empty space. And this empty space must have the property of supporting transverse waves. So it must be very thick. This was the ether that people thought was everywhere, and of course it was discovered that it is nowhere. So what is oscillating, I mean, it's very, in fact, what is oscillating in the vacuum? I don't understand the electromagnetic waves, and I think the more you think, the, you know, the less you understand, because it's an oscillation, but for a wave, we understand waves if you have a medium. Like on the sea, what is the wave? Is water going up and down, right? And here is air going like this. But in the vacuum, you have just the electric field and B field going up and down. But what is moving?
And in the when we draw like kind of
Yeah, but
we mean that the electric field and the magnetic field. We just write the
yeah, is the electric?
equation of the
Yeah, but still you like to see something going up and down. But there is just the electric field and magnetic field. In fact, people just do that, right? You know, electric and magnetic field. But what's going on? I don't know.